In this video, we're going to be talking about differential drive, which is a WPILib specific object that allows you to pass in your motor groups of your drive subsystem and get a few new ways to control and command your drivetrain. We're also going to be working a little bit more with subsystems and commands and talking about new ways of binding buttons inside of robot container. So we're first going to get started with setting up the differential drive object. And the whole reason why we're doing this in the first place again is to get new ways to control our drivetrain. So kind of like I alluded to in our previous video, tank drive is just one way to actually control a tank drive base. There's actually two other ways that we can control it, which we're going to be talking about in this video. So the first thing that we need to do to actually set up our our differential drive object is changing the motor objects that we're using. So right now you can see that we're using our Talon FX motor objects. And what we need to do is switch these to WPI underscore Talon FX objects. So I'm just going to quickly import this real quick so we don't get any errors. And all this is pretty much the exact same thing as the Talon FX object, but what it allows us to do is use Talon FX motors to interface with WPILib specific classes. Because what you're going to notice in a second is that when we instantiate the differential drive object, it takes in motors, and it's not able to take in normal Talon FX motors. It needs to be WPILib specific Talon FX motors. And this essentially allows us to pass in our motors so that the differential drive object is happy and everyone's interfacing with WPILib specific classes. So I'm just going to quickly copy and paste these to replace these all. And in general, it's great to use WPI underscore Talon FX because what this eventually will be useful for is code simulation, which we're going to be talking about in a future video. All right, so now that we've got that set up, the next thing we're going to do is declare our differential drive object. So public, and this is going to be public because we're going to need to be frequently accessing it, and it's just easier to make it public instead of actually making a separate accessor method for it. And I like to call it KDrive. You can call it whatever you want. So we've got that, and the next thing that we need to do is actually configure our motors to go back to their inverted stage, because what you're going to notice with these control schemes is that we're no longer independently controlling each side. Rather, we're following a similar control scheme to our first instance of coding a tank drive, in that we're controlling the entire drive base, both the left side and the right side, in unison. So the way to invert, if you don't remember it, is you invert your primary sides. So in this case, it can be whatever you want. So we're going to do right side primary, that's set inverted, and it's going to be invert type dot invert motor output. And then for redundancy purposes, I just like to make sure that my right side won, so my follower motors are also inverted. And the easiest way to do that is to just do invert type dot follow master. And we can do the same thing for our right side 2 motor. Oop, not that. Follow master, my bad. Okay, great. Now that we've set up our inverts correctly, we can instantiate the differential drive object. So we can say that KDrive equals new differential drive. And as you can see, get rid of these arguments real quick. We hover over this, this takes in a left side and a right side. So the first one's going to be left side primary, and the second one's going to be right side primary. So you can see already as Visual Studio Code wants to autocomplete, it takes in the left motor and the right motor. And in this case, we just need to pass in the primary motors because we know if we move those motors, then the accompanying follower motors will also move. Okay, now that we've got our differential drive set up, we're actually done in terms of what we need to do with our subsystem. So the next thing that we're going to be doing is making 2 new commands. The first one is going to be called arcade drive command. The second one is going to be called curvature drive command. So arcade drive and curvature drive are 2 ways in which we can control our drive subsystem. So arcade drive, essentially the way it works is that your left joystick and the up and down direction of your left joystick, so the y-axis on your left joystick, is responsible for moving your robot exclusively forward and backward. The right joystick, it's left and right direction, so the x-axis on your right joystick, is responsible for rotating the robot. So in the case of moving your right joystick to the left, that's going to move your robot counterclockwise. And if you move your right joystick to the right, that's going to move your robot clockwise. So what we're going to do is set up our arcade drive command. And then after that, we're going to talk about the curvature drive command and talk about why the two are different, even though they're a little bit similar in terms of their control scheme. So the first thing that we're going to do is set up arcade drive. So to do that, we're going to make a new command. Type in command. I'm going to call this arcade drive command. And this is actually going to be very similar to our tank drive command. So we're going to take in a drive subsystem and two double suppliers. And the first double supplier for arcade drive is going to be representative of the y-axis input on your left joystick. And the second double supplier is going to be representative of your x-axis input from your right joystick. So the first thing we're going to do is make our actual objects. So drive subsystem. We're going to make a double supplier. And we can call this, we'll call this translation supplier. And translate moving forward and backward. And we can call our other one rotational supplier, meaning that's the one that's controlling the rotation. Okay, now what we need to do is instantiate these by taking it in to the constructor and setting them equal. So drive subsystem drive double supplier P, and we'll call the other one double supplier R. Now we can instantiate them. So drive subsystem equals drive, translate supplier equals T, rotational supplier equals R. Finally, don't forget to add your requirements. Make this command exclusive to your drive subsystem. And there we go. So we're going to head over to execute. And the only thing that we need to do now is access the kDrive object inside our drive subsystem and call the arcade drive method that is built in to the differential drive object. So all it's going to be is drive subsystem.kDrive.arcade drive. And you'll notice it takes in two parameters, your x speed and your rotation. And now x speed is just representative of your forward and backward speed. That's why I like translate supplier better, because it's a little bit more general. So it's going to be translate supplier.getAsBoolean, or sorry, getAsDouble, and rotational supplier.getAsDouble. And there you have it. That's all you need to do. Now remember, we don't really need to do anything in initialize because there's no initial conditions that this command needs to have before it actually starts. And this command, we're not really concerned with its end condition because we know that drive commands generally run continuously for all of Telia. So now that we've written our arcade drive command, let's go ahead and write a curvature drive command. So in order to do that, it's going to be the exact same thing as what we've done before. Making a new command, right click, create new class plus command, type in command, call this one curvature drive command. And there we have it. So let's talk differences between arcade drive command and curvature drive command, because the way they are controlled is actually pretty much identical in that with both arcade drive and curvature drive, the y-axis of your left joystick is responsible for the translational motion of your robot, and the x-axis on your right joystick is responsible for that rotational motion. So the big difference between arcade drive and curvature drive is that the rotation that's commanded in arcade drive actually controls the rate of change of your robot's heading. Whereas with curvature drive, the rotation is almost very similar to the rotation of a car. So it's actually controlling the radius of curvature of your robot. So curvature drive is going to give you more of a car driving feel when you rotate, whereas arcade drive is pretty much responsible for controlling the heading rate of change of your heading. And sometimes arcade drive implementations actually only use one joystick. So the y-axis of your left joystick and the x-axis of your left joystick. So that one joystick both axes are actually used to control an arcade drive. So some people will actually prefer just using one joystick to command with arcade drive. So there's one extra thing about curvature drive that arcade drive does not really include. And that's the fact that curvature drive also allows you to rotate in place. Because if you think about it, right, if curvature drive is similar to the rotation of a car, then you know that cars can't really rotate in place, right? It's a little weird. But tank drives obviously can. You know, we've had experience with rotation in place with our tank drive command, right? So curvature drive also allows you to bind a special button on your joystick. And when you hold down that button and you start rotating, you can actually rotate your robot in place. So in order to do this, we're going to do a very similar thing to what we've done with both arcade drive and tank drive. So we're going to first instantiate our drive subsystem. Then we're also going to take in two double suppliers. So again, the first one is going to be representative of the y-axis of your left joystick. And the second one is representative of the x-axis of your right joystick. And we're going to call them pretty much the exact same thing, translate supplier. Let me just make sure I call that the same thing here. Yep, translate supplier, cool. Just so we have a similar naming scheme. And then private double supplier. And this one's going to be a rotational supplier. And then our fourth parameter will be a double supplier. Or sorry, not double supplier, a Boolean supplier. Because remember, the only state that a button could have is whether it's pressed or whether it's not pressed. So all we need to represent a button being pressed is a Boolean supplier. And we'll call this a rotate in place supplier. And we're probably going to need to import this. Here we go. So now we need to take in all of these and actually instantiate them. So we'll go ahead and do that. So drive subsystem drive, double supplier, T, double supplier, we'll call this rotation, and Boolean supplier, we call this rotate in position, or rotate in place rather. Okay, now we can actually instantiate these. So drive subsystem equals drive, translate supplier equals T, rotational supplier equals R, rotation rather, and then rotate in place supplier equals rotate in place. And don't forget to add requirements to make this exclusive to your subsystem. And there we go. Okay, so now to actually run this, it's going to be very similar to our arcade drive command. We're going to access the differential drive object that we wrote in our drive subsystem, and then call its curvature drive command. So it's going to be drive subsystem dot kdrive dot curvature drive. And you'll notice right here inside the parameters is that we take in the x speed, or the translational speed, the rotation, and Boolean allow turned in place. So we're going to go ahead and hit that. And it's going to be translate supplier dot get as double. Then we're going to have rotate supplier, or rotate in place supplier rather, dot get as, oops, sorry. This should be rotational supplier dot get as double. And then the last one will be rotate in place supplier dot get as Boolean. And there we have it. That's your curvature drive set up. So now let's go ahead and actually implement the curvature drive command inside a robot container so that you can test it out. So we're going to go to robot container, and we're going to replace the default command, which was previously set to tank drive command, with our curvature drive command. So I'm actually going to just change this to curvature drive command because we already know that this is similar, and the only thing that we're going to add is Xbox controller dot get raw button, and you can use whatever button you want. For now, I'm just going to use 1 as my button, which I believe is A. And there we go. That's all it takes to pass in and run your curvature drive command. So now that we've had some exposure to curvature drive and arcade drive, go ahead and test it out. Figure out a button that you like with your curvature drive. And one thing that I will recommend is that you're going to have to test and see if any of these axes actually need to be negated. And if they do, just slap on a negative sign right in front of it like that. So in order to test, what I would recommend is grab your left joystick first, start moving it up and down. If you move up and the robot goes backwards, that's an indication you need to negate it. And for your rotation, if you move your joystick to the left and the robot ends up rotating clockwise, add a negative sign. And you also want to make sure that when you actually press this button and rotate, that the robot's doing what it needs to do. So now that we've gone over differential drive, I want to use this video to also get in some more practice with writing subsystems and writing commands. So what I'd like you all to do now is pause this video and go ahead and write an intake subsystem. So our robot's intake, or rather our fake robot's intake, or the intake that we're working with right now, will feature one motor, so there's only going to be one motor, and the motor's port is going to be 7, and you need to write one method in the subsystem, and that method is going to allow you to set the percent output at which you want to run the intake. Then I would like you to make a command that runs the intake at 50% speed. So go ahead and write that. Be sure to pause this video and come back when you're done. Okay, so let's go ahead and actually write that subsystem now. So we're going to create a new class for this command. This is going to be a subsystem. We're going to call this intake subsystem. And all this is going to be is just one motor, so private. And again, let's use WPI talent effects. Intake motor equals new WPI talent effects. And like I said before, ID 7. And inside the constructor, I just like to do a config factory default. You don't really need to do it since we're only using percent output control, but I would recommend it just in case we end up needing to do anything else with this motor in the future. And then we're going to make a set intake speed. And let's take in 8% in our method. And then all it's going to be is intake motor dot set control mode dot percent output, and for our percent value. Great. Now we're going to write a command for it. So command. Do that again. Just need to make sure it said command there. Here we go. We'll call it run intake command. You can call it whatever you want. And this is just going to take in the subsystem. We're not actually concerned with any buttons in this case, because as I'm going to show you next, there's actually going to be an interesting way to bind this command to a button. So all we need to do is just take in the intake subsystem because I specified a speed. So speed's not going to be contingent on any joystick movement or whatever, right? So intake subsystem intake. Actually, I call this intake subsystem. Let's be a little bit more specific. Intake subsystem intake. And then we can say that intake subsystem equals intake. And don't forget to add your requirements for the intake so that this command is exclusive. And all we need to do is nothing in initialize, right? Because there's nothing that needs to happen before this command, or the second the command is initially run. It's just going to be run and execute. So we're going to do intake subsystem dot set intake speed, and we're just going to pass in 0.5. Now, this might need to be a negative value depending on how the motor is mounted or how you actually want your intake, quote unquote, to function. So if you need a clockwise rotation or a counterclockwise rotation, depending on that, you might need to make this value positive or negative, but for now, we can make it positive. So let's talk actually running this command in our robot container. So what we've done so far is only use joysticks to actually run our commands. And if you remember as to what I said before about configuring button bindings, you can't just do something like new run intake command, because first of all, if you actually do this, it's just going to run this command and it's never going to be binded to any button. So in order to specify the button that we want our intake command to run on, we need to use something called a joystick button. Now, a joystick button is a way for you to add a specific button to WPILib from your controller. So let's just instantiate it, and hopefully you'll see how it actually works. So private joystick button, so right here, and we'll call this the B button on our Xbox controller equals new joystick button, and it takes in a joystick and the actual button number. Now, button B on an Xbox controller is 2, I believe. And again, you can replace this with any other button you want. A, B, X, Y, any bumpers, any small buttons on your controller, etc. As long as it's picked up on the driver station. And you can double check your driver station for the IDs. So now that we've made a specific instance of a button on our controller, what we can do is actually control it. So there are a few different ways that we can actually interface with a button. One is you can toggle a button, meaning the second you tap a button, the command will run. And if you tap it again, the command will stop. You have the ability to just, the second you press the button, it'll run the command, and that's it. Now, you have to be careful with this setup, and because that we usually use buttons that require one tap if you have a defined end condition in your command. If you don't have a defined end condition, then I would not recommend just tapping a button and running a command. Usually what you'd rather do is toggle, or, and what we're going to do right now, is while held, meaning so as long as the button is held, the command will run. So all you're going to do is specify the button, so B button, dot while true, meaning while the button is actually held, we're going to run our new run intake command. And what we forgot to do is actually specify our intake subsystem and instantiate it. So we need to do that. So it's just going to be private intake subsystem equals new intake subsystem. There we go. And in this command, we can pass it in our intake subsystem. Now again, holding is not your only option. You can also do toggle on true, which means the first instance you press the button, or the first time you press the button, it's going to run the command. You press it again, it'll stop running. But usually when we control something like an intake, it's usually a held. And so while the B button is held, we run our intake command. And that is how we use buttons, or how we bind commands to buttons inside our robot container. So go ahead, get a feel for using different buttons. Hopefully you can take some time and instantiate a few other joystick buttons and give it a try. Try toggle, try held, or while held, really see the difference. And yeah, that about wraps it for this video, and hopefully we'll catch you in our next video.